Alrighty, we need to cover a lot of content. Not a lot, but a decent amount. We only have about 35 minutes. So let's get right into it. My audio is working. So this is lecture 16. We're going to continue on chapter 8. And we're using Munson's textbook. Some of the slides I referred from Dr. Abadi's. Okay, just to cite sources. Okay, I think that is it. So agenda today, we did group presentations. That went a lot better than I expected. Everyone did a really good job. Like I said, instead of having 2 midterms, this is supposed to be fun. And I think everyone's learning a lot, which I think is great. So it's like a presentation you actually want to kind of pay attention to and learn something. And for anyone that has like on the lower end grades, this project should help you. Right, I'm not promising like any grades right now, but they should be pretty higher average than what a midterm would be. So that should help a decent amount of people if you're concerned about grades. Okay, so let's do announcements really quick. So every single lecture, you guys will probably show up, right? Because I don't usually take attendance, but we have something going on every lecture now until we're done with the class. So next Monday, we have quiz 6, right? It's going to be all the Pi-Buckingham theorem stuff. It should be a pretty straightforward quiz, I think. But what I learned from quiz 5, it might not be. But I think it's straightforward. And I keep thinking about quiz 5. It's so funny because I feel there'll be a story you guys will all talk about later on. And you'll never forget Navier-Stokes equation, right? But like I said, I'm planning on curving that quiz anyways for people who are not here. Okay, second half group presentation. It's going to go exactly like how we did it. That's going to be next Wednesday. Okay, and then the following Monday after that will be homework quiz 7. That's the last quiz. And I'm leaning towards like pretty much going off of one of your homework problems for that because you have a final right after that. And this helps you study for the final, right? And then homework quiz 5, I still need to work on grading. I want to have it done before next Monday before I give you your new quiz. I had to work on writing quiz 6 so I could print it out today. So, okay, any questions on announcements? Yes?
For quiz 6, are you going to tell us what the repeating terms are, or do we have to figure it out? Because it's kind of a hassle if you get one wrong.
I wrote it, and so the problem that I had didn't have the repeating variables. I was nice enough to just give them to you already, so it's going to be on there. But I do not want you to not study how to do them, okay? It's just still know how to get those. So yeah, they're on your quiz coming up next Monday. They will be on there. Yes?
Are we allowed to write the steps, how to solve on the equation sheet?
Yes, you can do steps. That is more than fine. I was thinking about requiring everyone to do each step, which you probably have to do anyways on the quiz, but I don't think I will. What I'm going to do is if there's pi terms, I'm going to have like this pi terms is worth this amount of points. If you make a small algebra mistake, it'll be like -half to 1 point, something like that. So if you're quick and you don't want to write each step, that's okay. So I'll grade it kind of if you get your solution and the steps in between. Yes? Oh, guys are really pressing me today. I think I'm going to be nice and probably not do that. But you should still know how to get them. Just because hopefully I'm not being too nice this quarter. All right, Logan.
For quiz 7, are you going to be able to post the answers before the final so we can study with it?
Good point. Yes, I will do that. Yes, I'll do that. I'll have it ready. Once we take it, I'll post it. Yes, Tristan?
For the final exam, like similar to the midterm, would we be getting a list of topics that would be on there, just for study reference?
Yes, I plan doing that. I will do that in maybe one of these 2 days. I'll do that. I'll go over that. Yep, I will do that. Yes, John? I'll go into more details, but I am planning, we could probably do back and forward because there's a lot of stuff we learned and a lot of writing. So I'm probably go with 1 page front and back. Yes?
At some point before the final, do you think we actually finding the repeating variables? Because I'm still having a hard time. It kind of feels like a lot of informed guesswork.
Right. We can, but right, we're leading towards not. They're going to be given anyways. So, if we have time, I don't know if we will. But to be fair to you guys, I will give them to you on the final. Okay. Yeah, and that's why I made that specific slide for step 4, if that's helpful. But if there needs more clarification, you can send me an email. But from what I remember too, it's kind of a lot of guess and check. But you have those hints to help you find it. So I might not have time. If we do, I will. But like I said, I'm leaning towards like your quiz. I'm going to give them to you. So I wouldn't stress about finding them. Yes?
How do we know when to use like the FLT versus MLT?
You could use either. It should work out both ways. I stated in your quiz which one to use. The big one is there is a conversion, right? The FLT to MLT conversion. It's just Newton's second law in units. So if you have to go back and forth, that's there. For the quiz, I would recommend, I picked pretty standard variables. Like if you needed to know pressure, right, that's just force over area, right? So that's F over length squared. If you really wanted to, you can have a 1-page equation sheet for this quiz on Monday, and you can have that whole table from the textbook that shows each variable of what is it in MLT and FLT system, because that's step 2, right? And I do not give you step 2. That's clear. Yes?
What I noticed for FLT and MLT, if you pick one, sometimes doing the scaling will be really difficult if you pick the wrong one.
Oh, I see.
So on, I think it was homework problem 5, I wasn't able to, I had to convert before I could do the scaling.
Oh, okay, gotcha.
Otherwise, so you kind of only know after you
Do it. Okay, and that's for like the modeling equations, right? Okay, it's good to keep in mind. For your quiz, I say which one to use, and it works. So, good point out. Yes?
So is the final comprehensive?
Yes, whole class.
What percentage of the first midterm stuff is going to be?
I will go over that more once I do that study review date that Tristan's asking for. Alrighty? Good? See what time. Okay. I recopied and pasted. We're talking chapter 8, right? So my goal today is to kind of cover the rest of the concepts that we need to solve problems and do your homework. I will not be able to do an example until next Monday, because we still need to go through concepts. And I thought if we had concepts, I don't want to rush an example. If I get cut off on the example, I didn't want to do half here and then half Monday. That might be not beneficial for you. So we're going to try to get through all of the chapter 8 content, right? All the equations you need. You can start homework, head start if you need to, but then I will do an example the next 2 lectures. It's kind of hard, like I said, because every lecture now we have a quiz or presentation. Okay, so I'm not going to go through this again. I'm skipping a lot of these slides, right? We basically learned that there is a Bernoulli equation applied to these pipe flows. It started off with this equation with alpha, right? And that just shows your velocity profile coefficient. If it's non-uniform or uniform flow, we will almost assume alpha is always equal to 1. So that goes away. We have your normal Bernoulli's equation, and we're really just looking at this head loss for head loss minor and head loss major, and that's what we're going to talk about today. And this is like, if I were to put this on quiz or exam, which is important because this is what we're talking about, right? This is the main difference and the most important concept in this equation, because we're already used to Bernoulli's without any friction loss, right? So this is the friction. And we're going to go into detail about that. We already talked about, really quick, right? Friction factor is just it came from a Buckingham pi theorem, right? And we solved it. Friction factor is due to friction inside your pipe wall, and it's different for laminar flow and turbulent flow, okay? So laminar, it's this equation here, 64 over Reynolds. Reynolds number, which we already know, right? Mu over rho dV. If it's turbulent, you have to use this Moody chart, right? Which I already explained. I am contemplating about maybe having you look something up on this Moody chart, if maybe for an exam, because this is pretty important. Like I said, this was on my FE exam. So it's a pretty popular chart. And I believe for the homework, it will ask you to look up these friction factors. So I haven't written the final yet, but if time is constrained, if I feel like you're not enough time, I will just give you the friction factor or something like that, or make it a quicker step. Maybe you'll be like, okay, these are your values. Just find it on the chart that correlates here. It'll be really obvious, something like that. Okay, and now we get to the new stuff. Okay. Are there any questions on the topics from last lecture? Okay. And the reasoning why we're doing this friction factor, because this goes into your major losses for head loss major and head loss minor. Okay. So let's talk about head loss major, right? And again, I keep repeating myself, but this is major, this is minor. We're going to talk about these two today. Okay, so head loss major is loss due to friction against the pipe wall, okay? So if you look at these diagrams, this is just conceptually, right? There's your XY axis. Viscous sublayer, that's just the layer of what you're accounting for in the roughness of your pipe. So if you zoom in here, you see that this roof wall, right, epsilon comes from right here, your equivalent roughness for pipes. This is the material of the pipe, and this is epsilon. It's just a table. The main reason for this, right, for your Moody chart, you're going to use it on this axis here for these. Okay, so this is a rough wall, you can see, a more smooth wall, and you can see the velocity profile changes, right? So it's a little bit less once you get to the closer to the pipe wall, and it increases once you're in the middle, which is pretty intuitive, right? Once you get to the center of your pipe, that's when the flow is the fastest. Okay, the friction against the pipe wall we represent as tau with the subscript W. I don't think we use a lot of that in your homework or anything, but I just wanted to mention that. Let me make sure my mic is working. I don't know if anyone looked back at my old lecture last week, but the mic died. Okay. Friction factor must be calculated depending on laminar or turbulent flow, which I showed you kind of earlier, right? If you have to use the Moody chart or the Reynolds with that 64 number. Shear stress for turbulent flow is a function of density, but for laminar flow is independent of density. So that's a big difference between the two. It's one is a function of density and one is not. The main function of laminar flow is viscosity, mu. And same thing, I'm going to skip the derivation of how we get this equation for head loss major, but it comes from another Pi-Buckingham theorem, and you get your pi theorem. That with the mix of Bernoulli's equation. So that's in the textbook if you want to see it. I'm not going to fully derive it because we've done so many Pi-Buckingham theorems already. So this is your equation, right? This is the one that you want. So this is head loss. Okay, this figure kind of just shows where the Pi-Buckingham theorem came from, right? You have your pressure drop from 0.1 to 0.2. You have your diameter, and you have your velocity. This is your roughness, epsilon, density, and viscosity, right? And I think I kind of mentioned all of the variables in the equation already, except gamma, which we all know, right? That's just density times gravity. That's specific weight. Okay, I looked at an equation. We should know all these variables here already, right? Friction factor is F, we talked about last lecture. Oh, and it even goes to detail here, right? So laminar flow, like I said, friction factor is most of the time 64 over Reynolds number. And for turbulent flow, right, you have your Moody chart, which I showed you, but these are kind of the equations for the curves that you can plug and chug. If I ask for a specific one, I'll definitely state it. Right, the difference between these two formulas, this one is hard to solve for because there is a square root f within a log. So to algebraically rearrange this is a bit more difficult. This Holland equation, hopefully I'm pronouncing that right, the friction factor is right here on the denominator. So right, like I said last lecture, you just multiply it over here. So it's on the top, this goes on the denominator, square both sides, and then you get your friction factor there. Or you can visually do it with the Moody chart. Yes?
Is there going to be a case where gravity is 0?
Should not be, or else we would get a bad denominator, right? Because gravity would be in here. So, and we're always on Earth, so we'll have gravity. Okay. Good. Okay, minor losses. So this has to do to loss due to piping components like fittings, valve, bends, tees, like in the dialysis presentation that we listened to, right? They have maybe some fitting components in their system. So there are some losses associated with that. So for example, we can just skip into this diagram, right? This is your standard valve, right? Righty-tighty, lefty-loosey. Here is like a kind of a cross-section view. When you tighten it with your threads here, it pushes it down to obstruct the flow. And the moment you loosen it, right, that's when the flow kind of releases and goes through. So it would flow through a valve as common minor loss. So the head loss, we already talked about that. The head loss for all components are given in a dimensionless form based on experimental data. So everything that we're going to talk about here for these fittings, they're dimensionless, kind of like our Pi-Buckingham theorem. All of them, you'll see the graphs and stuff, they're just been tested by laboratories. So that's how we're going to get those values, and I'll show you. And the big thing about this equation is your K subscript L. That is your loss coefficient. So that is basically the common method to determine your head loss for each component. So it's different for an elbow, it's different for a valve. I wouldn't worry about these equations too much up here, but if you need them for homework or something, right, KL is right there. It's your head loss minor divided by velocity squared divided by 2g. And you can see you put in your pressure drop in there, delta P, if you need it, and you can solve algebraically here. The main equation you want is this, because this is what you're going to solve for when you plug into your Bernoulli's equation. Okay, so the minor loss coefficient, the KL that we need, you will usually get from these graphs and figures, right? And like I said, these are all experimentally tested already. And when the moment you hear experimentally tested, you want to think in your head, ding, 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 right? These are all not fully accurate, right? Because the person's experiment might vary from what you're working on. So just keep that with a grain of salt if you ever have to do this for work. So here, right, we have different scenarios. You can just see like these are basically flipping, right? Your area 1 is greater than your area 2, or your area 1 is greater than area 2, or your area 2 is greater than your area 1. So you take the ratio of that, and then this is the experimental data that they made curves for already. And it's pretty straightforward, right? So you find your areas, calculate it, go up, find this, and then you find your KL. And then some of them are already preset. So if you have an elbow, right, at 90-degree flange, you have a 0.3 KL. So you multiply that in your head loss minor equation. This is table 8.2. You can look at all of the different piping options, and your KL varies. So looks like, let's see, what's the highest number here? Looks like
210.
Yeah, 210 right here. Gate 1 4 close. So you can see it goes all the way there. Look, this one's not good, right? This is infinity. So this is if it's given already for you. Okay, non-circular conduits. We actually talked about this a few weeks ago, right? And the term conduits, that's just either your pipe flow or your square tube. So it's kind of weird. The textbook refers to it as non-circular. but this is just basically a annulus, which is a tube, but it's only like a donut. There's only water coming around it, not in the middle. So I did not see any homework problems. I don't think I actually posted the homework yet anyways, but there's not any homework problems on these, but I wanted to mention to you, since every single thing that we've been explaining for this chapter is all your standard pipe, this is if it were not to be a standard circular pipe. So last lecture, I derived this equation for you to show where friction factor is from. And if you remember, there was a constant C that was 32, and that was just for your traditional circular pipe. But now that C changes for a annulus or a rectangle here. So you see the C here changes right there. So that's how your equation changes, and then you have your parameter d1 over d2. Hydraulic diameter we talked about before, right? That is just your 4 times area divided by the wetted perimeter. Here is a side view of your velocity profile with that. And when you have these, right, your Reynolds number has to use this hydraulic diameter. It can't be your traditional diameter. And all the D's here change to this hydraulic diameter. And I also wanted to mention this because I remember in my FE exam, this came up too. So equations look pretty similar, right? The only thing difference is this hydraulic diameter, which is 4 times the area divided by the perimeter. Rectangle, if you had like a duct for HVAC, your hydraulic diameter is this equation, right? Which is depending on the width and height of your rectangle there. Okay, and like I said, I did not really see problems on the homework for this, and obviously if it's not on your homework, or it won't be, I'm not planning to put it on the mid final. I just put it here, like I said, if it talks about in the future or your FE exam, you kind of at least have an idea of what it is. Okay, we're doing right about time. So here are different type of pipe flow examples. We have a single pipe, or we call it single pipes if there are multiple single pipes. That's exactly what we've been discussing this whole time. There are multiple pipe systems. There are pipes in series and pipes in parallel, which I'll show you a figure of. That's kind of like your circuits, right, that you've done in physics 2. And then we have loop systems, which is, I'll show you in the next slide, but it's just 2 pipes connecting into one cross section. And a general pipe network, that's just a really big system of multiple pipes with inlets and outlets. So, sorry, I'm kind of rushing here. I want to make sure we have enough time. Single pipe systems, you can categorize them as specific types. And the only helpful reason for this is sometimes in the textbook you'll see this problem is type 1, this problem is type 2, or this problem is type 3. So the main difference is they call it given or determine, which is basically your given and finds in your engineering solution. So your given is when your parameters are independent, they're given to you, you have them. And the determine is dependent on that independent variable through an equation somehow. So sometimes you will need to do a trial and error solution that are usually required when the direction of flow and friction factors you might not know. So you can see here, right, type 1, you have all these knowns that you already have, but you need to determine pressure drop. For type 2, you have all these givens, but you don't know flow rate, right? Okay, maybe hit on your quiz, is this flow rate? You might want to know the dimensions for that, right? That's just your volume over seconds, so that's length cubed over seconds, okay? Type 3, you have all your givens here, you need to know diameter. So this is just showing, in the textbook you'll see, this problem is a type 1. You'll know, you need to determine pressure drop. Okay, here's more interesting things. This is a multiple pipe system. So this is a pipe system in series. So you can see they're just like kind of connected here. And the diameter is getting smaller as you're going from left to right. Then you have your area. Q is your volumetric flow. Okay, so series pipes, you can assume that your volumetric flow rate, Q1, Q2, Q3 are equal. And then your head losses for the first section, second section, and third section, you can equivalent them just by adding them. And then pipes in parallel, your overall volumetric flow rate, you can sum up in Q1, Q2, Q3. And you can see these are parallel, right? Just tubes in parallel. Maybe kind of looks like a heat exchanger, kind of. So diameter could vary, but these are your diameters. So it's pretty easy to see, right, if they're in series or in parallel. And then here it's a little different. Your head losses are equal at each one of these tubes. So that goes back to physics 2 stuff, right? When you had circuits, you had your resistors, things like that. You have to add resistors in parallel or in series. So it's kind of a similar idea here, but with pipes. Okay, here you'll need this equation for homework. There is something called a multiple pipe loop system, or in short, it's just a loop system. And sometimes they'll find you, hey, what's the pressure or velocity or density at this node? But then it's a little bit different from what we've been talking about, right? Because we have a consistent singular pipe. This is outstreaming to 2 different pipes. So this just came to mind. I think the HVAC group asked me a question about your tube going into 2 directions. So this might have been more applicable, actually, if you had to use this. But that's okay now. I said you could set your assumptions right in your project, which is totally okay. So you can see you can write your Bernoulli's equation twice here. The only difference between these 2 equations is you can see that the head loss at the location 2 and the head loss at location 3, they are equal. Okay, so for loop systems, this is what you mainly want. Flow rate in the first section, when it branches out to the 2 other sections, is equal to the flow rate in your second section plus the flow rate in the third section. And then the head loss for the second and third section are equal. Like I said, there's a homework problem about this, so you'll need this. I think there's also a homework problem in series. I'll try to post homework by tonight, but I think you'll be studying for your chapter 7 quiz on Monday, so I didn't even think you'd study anyway, so for this. Oh, it is? Oh, I'm ahead of myself. Good job. Good job. All right. Yeah, you'll see I'm like posting, replying to emails like 1 a.m., so I just kind of get in the zone and do stuff. So, okay. All right, so here is a general pipe network. So this is what your pipes will look like, you know, in a city or underground, right? This is what you're used to. This is just connecting a bunch of pipes, right? You have your singular pipe, you have your loop system here, you can have them in parallel or in series. If you were to solve this, right, you would just take the node and then you would apply this equation here. And you would find these parameters here. And you'd basically just spam Bernoulli's equation over and over and over. You'd probably want to write a code for that. So we're not going to do something that's hard in this class. I don't think it's hard. It's just tedious. I just wanted to mention that. I heard there might be like an advanced fluids elective. Is that true? This is something that they might have you do. Maybe a little sneak peek. I need to fix that little quick typo. And that is about it. Is there any questions on content I went through? We're running just right about time. Okay, so we finished presentations today. We've pretty much finished chapter 8 today. We already know all the dates, so Monday there is going to be a quiz. I'm going to go print that out right now. And yeah, that is it. Thanks for doing a great job on the project and showing up today, everybody. I'm here for questions if you have it. So yeah, have a great weekend. Yep.